I had a couple of students stick around lunch yesterday, and I meant I said this or not, but they measured the room. They 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 did the cubic foot in the room. That's the room I teach in. It was 12,000, over 12,000 cubic feet. Um, I think it's one of the biggest rooms at Norman High. But then we did the process. Because every cubic meter of air weighs 1.2 kilograms, and so when you add it all up, and then you convert to units we're more used to, the air in the room. I'm not talking about the desks or the chairs. Just the air in room 807 at Norman High is 900 pounds. So with lift, with drag, we're talking about moving through, a car just cruising by. We're talking about moving through, thousands and thousands of pounds of air having to get out of the way. And we think of air as it's nothing, it's just there. But it isn't. It actually takes a toll on a car or a jet, just chopping its way through that. And it's like air at a high velocity. Air is like water. Water's approximately 1,000 times more dense. And water drag, hydrodynamics, is a whole nother issue, which involves more calculus. Air, you can get away with it without having to do too much calculus. But in fluid dynamics, you still are talking about, you can talk about gases through fluid dynamics. So today we'll talk about that some. We're not really doing today. We're not going to do drag and lift. We're going to do cycloids. Just whatever. I mean, I have a bunch of slides, and it's whatever comes up in first hour. However that discussion goes, I try and recreate it all day. All right, so we'll share the screen. Little sting music. Sting. All right. The Sting Man. That was an old Saturday Night Live. All right. Stingerator. Your parents probably know that one. Classic. All right. So the chat is somewhere. There it is. We had our monthly meeting last night. Now it'll be a weekly meeting for Ask Me Learning. I'm looking. I have 4 monitors, so I'm looking at that one over there. And we were discussing June, and I'm putting together. I have 12 sessions now that I'm kind of focusing in on for physics, and it's serious physics. We'll do it in a non-pressure, not the pressure of a typical class where the grades are all the thing. You're there voluntarily. I realize that. So we may have a live aspect to it because there's some things like we run stadium steps or some things that we need to do. Anyway, so more about that later. We'll start advertising it May 1st, May 2nd, May 9th. And I can give you more then. And I'll have a website I can send you to. They're working on the website. So we're on free bodies again today, but this time we'll do a couple of free bodies and then mostly looking at cycloids. Amazing thing happened today. This hadn't happened in probably 5 years, maybe longer. Second hour, every student had their homework done, 100%, and there was nobody missing. There was nobody gone, and every person that was there had their homework done. I thought, that'll never happen again. And then it happened again, third hour. It's like, that's called a clean sweep. That just doesn't happen. I mean, I sent pictures to the faculties like, whoa, of course they're jealous. They're jealous of me because I have the best kids. Sorry. Sorry. Yeah, well, you have best students, ASCII. So, of course. Hey, I mean, I go around and check. I mean, every day I take 5 minutes out of class and check and look every student in the eye that didn't do it. And why didn't you do it? See, I can't do that with you. That's why I don't, that's the only thing I like about. I can't get in your face. And I'm just kind of counting on you keeping up with your homework. So speaking of homework, you should have 5 and 6 done. If you're looking down at a blank paper, you're not playing the game right. And today went really well because they had already invested time and thought about it. They were wrong. I mean, probably, I don't think anybody was right, but that's okay. Get over it. Get over your ego, for God's sake. Be wrong. Yeah, be wrong every day. It's the only way you're going to learn. Be brave enough to make mistakes publicly, even. I do it every day. All right. So we're going to work on 5 and 6, and that's going to lead us to other discussions. So you'll also need this out. Io came by this morning, picked up a packet. There's packets on the front porch. It's like 15 sheets in there. And then there's your notebooks still. A lot of you have, I mean, I if I remember, I pull your notebooks in inside at night, but sometimes I don't remember. And those notebooks sit out there all night. Who knows what kind of hoodlums are out there looking through your notebook. So if you turned your stuff in a notebook, you got to come get it. It's on the front porch in a box. Okay. So here we are. The car slowing down. Hold on. Before we get to that, I want to show you this. So yesterday, those that were here, we watched the drag video, and we watched a lift video. Okay, not RuPaul. I mean, this is actually air drag video. And so these are the two videos. I didn't do screenshots. I could have, I guess, of the videos, but I can't really show the videos. I can't record that for copyright reasons. But these are the two videos. They're about 12 minutes or so. And I think it's worth watching. You're not requiring it, but if you're going to go on in physics or in engineering, you really ought to know about this, 9,000 pounds of air you're trying to, in this room I'm in right now, there's probably 300 pounds of air surrounding me that you got to get through. And then I included another 4 or 5 videos. One's on the dimples on a golf ball. I think I'll show it in class tomorrow. If I do, then we'll show it here. One's like from MIT. It's like an hour and a half, which you really want to get into. And then one's of this dude right here, this guy, Bernoulli versus Newton. I love this guy. He's kind of funny. He's an old dude, sits back behind his desk, and it's a good solid video on Bernoulli versus Newton. Okay. I mean, there's 2 different approaches to lift on a wing. People invoke Bernoulli's principle, which is false. It's not really Bernoulli's principle. And then people also invoke Newton's third law. It's some combination. Bernoulli's principle is involved, but that's not the only reason. People think, well, there's the reason. No, that's a little bit of it. A lot of it, it's very complicated. That's why MIT has an hour and a half video on it, just trying to get through it. Okay, so back to this. We have a car now, this same car. All of these have been the same car, so every MG is the same. And everything else changes. So the car's slowing down now from 120 miles an hour to 60 miles an hour. Still, though, going at 80. So once you see that it's going at 80, then you can go over here and just use this stuff because these forces depend on the speed. Okay, so it's going 80. So I know my lift and my normal force are going to be just like it was in number 4. Maybe this is why everybody had it done because these were already half done for you. Oops, normal force doesn't go all the way up anymore. As lift increases, normal force drops off, and force of lift. Okay. And air drag is dependent on V, right? It's a function of velocity. So it's going 80 miles an hour still. The air drag is still back at the same length it was in 4. So I'm going to guesstimate something like that. There's my R sub A. And friction is a combination of normal and the coefficient of static friction, which is the same in both cases. So friction, and it depends on normal. Well, normal depends on velocity because velocity depends on lift. So it all works out. All these kind of affect each other. So my force of static friction is back F sub S. So all those forces look the same. But now the car is in neutral, meaning you're not pushing the gas at all. So the one thing that changes is you don't have that F sub P anymore. You don't have that forward push, okay? And so that's it. You still have the DOM, the direction of motion is still this way, big DOM, and then put a little plus in that means the plus in the tip, meaning that's positive. So when I write the equation out, if I just looked at that and did not realize it was moving at 80 miles an hour, I would say it has to be because there's RA there and all, and there's lift. Okay. But it looks like it's going to the left, but of course it's going to the right and it's slowing down. So I have negative RA minus the static friction equals, now this time it doesn't equal 0 like it did up at number 3 because that was in this cruise control, but it is accelerating negatively. So it's MA sub X. Do not hardwire the negative in for A. Oh, I made that mistake one year. That is a disaster. Don't do that. Let the math tell you. I mean, obviously that's going to be negative, right? And then sometimes if you hardwire a negative in for acceleration, you get 2 negatives and it cancels, and what a nightmare. So this RA has to be negative, right? I made it negative. The drawing made it negative. FS has to be negative. M has to be positive because it's mass. Can't have negative mass. So the only way A has to end up being negative, which is what you want. Okay, so that's it for that one. Now we go to number 6. Now in number 6, let's do a little experiment here. In the chat, type in how many forces you think are involved. Give me a number. You don't need to list them. Just tell me how many forces you think are involved in number 6. Go ahead and type in what you think. Okay, I hear 5. 5. See, you all are daring to be wrong. You're daring to be wrong publicly. That's bravery. 6. 5. Okay. Very interesting. 5 again. Okay. Anybody else want to play the game? And Sophia dropped down to 4 now. Bennett dropped way back down to 3 now. And if you look up at the top, this probably helped the game. If you look at the top in the purple up there, that's the only forces it can be. Okay. And also on 5, 6, look at this thing. Look, here's the key to a lot of this. That right there at 20 miles an hour. It's a snapshot. We're on our way. We're at 60. Well, we're now sliding to a stop, and we're almost there. We're at 20 miles an hour. We're going from 60 to 0. Okay, now the numbers are coming down. And Bennett finally hit it. So Bennett gets the point there. It's only 3. There's only 3 forces. Up here in the purple, there's only 3 that we would use. There's no force of push, right? It's not being pushed down the road anymore. There's really no force of lift at 20 miles an hour. No, you put your arm out the window at 20 miles an hour, you're not going to get blown back. No buoyancy, obviously, no wind involved, no thrust. It's not a rocket. There is friction, there is normal force, and there is weight, and that's it. Just three. Don't feel bad if you were overshot it, because people did in class too. We went to the board in third hour anyway, and people were overshooting it. But that's cool. You got to learn in physics to make mistakes and enjoy those mistakes. Wow, I get a chance to learn. Now, okay, so we have friction back. Now it's kinetic friction. That's where we're spending a lot of time talking about this, the difference in kinetic and static. But we have kinetic friction back. It's huge because you are slamming on the brakes, right? You're locking up your tires, F sub K. Okay, so now let's do the normal force. What do you think? Anybody want to argue with me on that one? This is the normal. You want to argue with the normal in the MG being congruent?
Since I don't know if we're going this far into like taking everything into account, but since the brakes are being hit and the car is like slouching forward, would that have any effect on the end?
Yes, and that's a couple of discussion points there, because that is true. If I'm standing on a scale, and it's an analog scale with a needle, not electronic scale, analog scale, it measures me, and it'll measure me at 190 pounds. But I could jump to 210 pounds simply by pushing down, pushing on the earth, pushing on the scale pushes back on me. What a scale does not measure your mass or your weight. A scale measures the amount of contact between you and the scale. So really it measures the normal force. If you put a scale at an incline, you'll weigh less. And we'll get to that more later. But you are correct. The normal force here is going to be slightly greater, maybe by 100 pounds. I mean, a car is, we're looking at, 2 tons, whatever, or say 3,000 pounds. So 100, 200 pounds. I can up my weight by 20 pounds or maybe 30 pounds by just forcing myself down. And that's what happens in a car that nose down as you're slamming on the brakes, and it's putting the contact now because you have that downward force at an angle, the contact between the car and the street is increased. So you can't make that'd be a point, a couple points off on a test if you made those two congruent. You have to show congruence or you lose points, but here there's nothing that's congruent. Okay, that's good. Good job. So that's it, just those three forces. Now the direction of motion is still this way, but then when people went to the board, some of them were still wanting to put a front arrow, and there's no force to push. Well, I had a student do this. They did this. I said, well, yeah, I know, but that's the momentum. That's low P. And the answer is no, you can't. I'm not saying there's not momentum. There is momentum forward, but this is a free body diagram. Free body diagrams you cannot put other vectors on there. If you do, you can list stuff. Like I can go ahead and say, well, I'm going to list the idea that just so I know, in my head, oh yeah, there's momentum, but you can, so but you can't make that a vector on there. Only forces can go on free body diagrams. So now the equation is negative Fk equals max, and that's it. Okay, very good. Well, that completes the front, but now we got to talk about this Fk versus Fs. All right. Yeah. Okay, so now you need a piece of paper. This is part of your cheat sheet, and I'm telling you right now, this will be on test. It'll be on test 6A, and you don't get a cheat sheet for that one, but it doesn't hurt to write it down. And it'll most likely be on test 6B as well in some form, because it's a pretty important concept. I mean, covers of physics books are of this stuff we're about to talk about. Now, I think there must be 100 YouTube videos about this stuff, just from me just perusing YouTube. Okay, so draw yourself on your paper, draw yourself a line. Go go ahead and kill a tree here, make it pretty big. And then we're going to draw 3 circles. This is where having an iPad comes in handy. So you draw 3 circles. Okay. And maybe I had in class, we had cups. And so every kid had a cup. And we were using the small end of the cup. We use the large end of the cup for this one. Now, these circles need to be the same, as close as you can get it. Duplicate, duplicate. So, and you want those circles to line up like this. Now, this is a Newton thought experiment. Here's the question. As a tire rolls down the road, as a car is rolling down the road, I don't have a tire, but we use the CD here. So this, or this DVD here. So if we are rolling down the road here with this DVD, if I'm just spinning the DVD in place, if I just spin it in place, then that's pure rotation. If I roll it down the road, though, rolling is not the same thing as spinning. So now it's spinning and it's rolling down the road. And so Newton started looking into this, and he discovered that the axis of rotation, where do you think the axis of rotation is, right? For this CD spinning around, or a tire. Where is the axis of rotation? It's right here in the middle, right? It's where my finger is. But if it's rolling down the road, where's the axis of rotation? And Newton said, say it again.
At the bottom of the circle.
Right. Newton said that a tire that's rolling down the road is rotating about this point. What the? Oh, okay. Get rid of that. It's rip. This thing has been dying on me all day, and then I got to start over again. I'm taking this to Anna Moore here in about a little less than an hour. See if we can get this thing fixed. Okay, so maybe. Okay, so what Newton said was, he said, no, this is the axis of rotation. A rolling tire rotates about that point. So the whole tire is rotating about that point right there. You like that? Heck no, you don't like it, because it goes against common sense. So Newton does not like being called a fool. So now Newton's going to explain. So now let's start off with, remember there's 3 types of motion. To remind you here from an old conversation, 3 types of motion. We talked about it as a father telling his kid to stop running around the house, right? So he tells him to go sit in the corner or stand in the corner. So what the father did was he got tired of the kid's translational motion. So translational is moving from point A to point B. Okay. So the kid stops doing that, but then the kid gets the idea. So he starts rotating, right? Starts turning around, spinning in place. And that's rotational. So the dad says, stop rotating. Then what can the kid do? What's the third and final type of motion? This is a conversation we had about 2 months ago.
You can go up and down.
Okay, up and down, sideways, back and forth, and thank you. And that's called vibrational. Now, on vibrational, your center, so you can't really jump up and down, but you can squat, raise. Your center of mass shouldn't change much. It might slightly alter, but it shouldn't change much on vibrational. Now, this is Newton. He's not going to talk about vibrational here. We're just going to talk about We're talking about translational rotational. Okay, so this tire is on the road. Let me move it down a little bit. Okay. And if it's pure rotation, and in class I have this big wheel, and I spin this big wheel, okay, pure rotation. Then, and let's say we're rotated really fast. So the top foot's going 60 miles an hour. And let's say it's rotating clockwise. So V, this is not a force vector, but V at the top is 60 miles per hour. The axis of rotation, this is pure rotation, it's not moving. And so what about the bottom of the tire? Right? It's still 60 miles an hour, only the other way. Well, we'd say, I guess we could say that's V equals negative 60 miles per hour. Okay. Sometimes it's redundant because it's going, the arrow shows it going backwards, but just to emphasize that, I'll say negative. Okay, now take that tire, that CD, if that's what it is, take whatever that object that's rolling, and this time don't roll it, just slide it. So we slide this hula hoop in the room. You slide it this way. Now it's moving down the road, but only in translation. So this is called pure. Remember, we're thinking like Newton now. This is called pure translation. Pure translational. And if it's say it's moving down the road at 60 miles an hour. Well, if that's the case, top, middle, bottom, the top is going 60 miles an hour. V equals 60. The middle is going 60 miles an hour. The whole thing's going 60 miles an hour. The bottom is going 60 miles an hour. So these are all congruent, 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 congruent. 60, 60. Okay, now I'm going somewhere with this. And I'm sure they were going, come on, Newton, get to your point. Okay, well, this is now rolling. When a tire rolls, it's a combination of rotation, and pure translation. So I add these vectors up, addition of vectors, right? And when I do that, the top now is moving at 120 miles an hour. V equals 120 miles per hour. The middle, 0 plus 60 is 60. The middle's moving at 60 miles an hour. And the bottom, negative 60 plus positive is 0. It ain't moving. So where the tire touches the road is the only part of the tire that's not moving. Everything else is rotating about that point. Now, a microsecond later, it's rotating about another point. But that point, for that instant, that snapshot, everything is in the process of rotating about the bottom. Oh, another thing before we move on, another thing that comes out of that is, now this helps because that lets me know that this is indeed F sub S because it's static. It's the only part of the road versus tire, relatively speaking, is static, no motion for that instant. So the top of the tire is notice if you're driving down the road at 60 miles an hour, the top of your tire is going 120. So your tire actually goes from 0 miles an hour static to 120 miles an hour, the part of your tire, in a fraction of a second. You think of a tire going down the road, we could actually determine the radius of the tire, how many times it spins. The RPMs is huge, rotations per minute, rotations per second even. Well, depending on their circumference. But that's going, in less than a second, it goes from 0 to 120 miles an hour. Now that puts a tremendous amount of force and stress on a tire, so they eventually blow. Take, for instance, Indianapolis 500, where they're going, in Indy 500, you're going 200 miles an hour. That means the top of your tire is going 400 miles an hour. That means parts of your tire go from 0 to 400 in about 10 milliseconds. So whenever they pull in for a pit stop, right, pull those tires off, put new ones on. All that heat it generates and all that torsional, all those twist, it's called a torsional force. There's a torsional constant, it's kappa is its symbol. But it's this idea of twist in the tire. And that eventually breaks it up, even though it's steel belted. You know, they can only take so much stress. There's things called stress moduli. So here's what I did in class. Yeah, it's everything we did in class. Okay. So we're good so far. That's still not the weird part. Now we go to this other thing. Now you're going to draw it again. You're going to do do another line, and this time, if you have a cup or something small, like maybe a pill bottle, okay, a prescription bottle. And here I have mine. Just grab a prescription bottle or something. Go grab one. Come back, and we're going to draw as many on that sheet of paper. You're going to draw as many of these as you can lined up. I'll show you what I mean. Okay, I'll line these things up. Draw one. Okay. Yeah. So there's one. Now, I'm going to duplicate that a bunch. And I know I need to write this worksheet because although I think it's kind of fun to do a little arts and crafts for once in a while. So I'm duplicating it now. Now I'm going to move these so they're all lined up on that row. This is all, by the way, this is one tire. One tire, and I'm looking at it. I'm looking at it at different times as it's rotating. I'm going to follow the rotation of this one tire. Okay. Jeez. No. So take your time. I made them all use cups. Arts and crafts physics. Okay, that's probably enough. Okay, let me give you a minute. And if you're watching the recording, hit pause. It's worth doing this because this is huge. Like I say, there's probably 100 YouTube videos on this. It's the first people to really notice this were the Persians, Tusi. The Persians dominated early science and math. Before it became a theocracy, Iran was a leader in the world in science and math, mostly math, and astronomy, by the way. They had one of the world's first observatories was in Persia, which I guess modern day Iran. There's a whole sector of Persians who are pissed about this theocracy, and they want to get science back into Iran because they want to go back to lead the world again. They're brilliant people, but that's what happens when theocracies take over. First thing that goes, knowledge. Mm-hmm. That's why in America we separate them, supposedly. Okay, now So my point was, this is Persian initially, and then Western Europe. The first one to really start thinking about this was Galileo. He didn't understand it, didn't have the algebra, but then Newton later figured it out. But hold on. So let's show you here. Now take a preferably colored pencil if you have it. Let me find a good color. I'll go purple, maybe. Purple, light purple. Purple. How about light green? There you go, green. Okay, so now take a point. We're going to put a dot on that. Make it a good sized dot on that tire. And now we're going to follow that dot as that tire rotates. We're going to follow that dot, and every one of these represents 1/8. Each one of these represents 1/8 of a turn. 1/8 of a turn for each drawing. Okay. So then in 1/8 of a turn, now my dot is there. In 2/8 or a quarter turn, my dot is here. Okay. 3/8, 4/8 or half, it's back top dead center. They call that top dead center. Here it's at 5/8. Okay, you get the idea. 5/8, 3/4, 7/8, and 8/8. I'm back to where I started. And now we start the process over again. 1/8, 2/8, 3/8, half, 5. That's as far as I got.
Is this going to be a cosine wave or something?
Good guess, but no. I remember I thought the same thing when I first did this in college. Thought, oh, whoa, it's a cosine wave. No, it's something much more interesting. Now let's connect these up and connect your dots, not dot to dot. Realize the curvature involved. Give me a smooth curve. I'll go blue. I'll go light blue. Hold on. You do it too. Orange. Okay. So here we go. Ba-doom. So I'll connect these up. Here we go. Connect up to the peak and then come back down. Notice it's coming down and slowly. And then it's going to stab the ground. Stab. That is a stab. It's called stabbing the ground. Stabs it. And it's heading back up again. Boom, 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 boom. So it's not a cosine wave, as you might guess. It is called a cycloid. Now, this is actually on the cover. This cycloid pattern, you'll find on the cover of different physics books. Cycloid pattern, I have animations of this. Hold on. Okay, I got a whole bunch of stuff here I want to show you. So there it is on my website, and I'll put a link to this. I have an animation of a cycloid pattern. I've got to go talk to Anna, but when I get back later on this afternoon, I'll put a bunch of things, a bunch of animations and videos. Like I say, there's probably 100 videos on this. I'll pick a few out. There's like Mythbusters and Vsauce, and so all these on this pattern. And you go, who cares? So what? Well, it turns out you see this everywhere. For one thing, you see it in nature. Here's a sunflower. See how the sunflower, how they grow, how these things tend to, like in nature, you find the golden triangle, the golden ratio all the time. You also find cycloid patterns all the time. It's how plants grow in these cycloidal patterns. So it's
See the Fibonacci sequence a lot too.
You see Fibonacci numbers, you see Fibonacci sequences. These are all these things that are just common in nature. Here's a kind of, okay, there's something that's out of a textbook, but showing, but I just got finished showing a bigger version of it. But here's a professor. This guy's pretty cool. I'll look for this video. But what he did was he made his tires square and then put a cycloid pattern on the ground. So he flipped it, right? And as he rides his little tricycle there, it's amazing. It's like weird. It's like you're seeing something ain't right. He's riding smooth. He rides smooth over the cycloid with square wheels. It's a sight to behold. I need to see if I can find that one. You go, well, okay, that's all interesting and all, but so what? Okay, so like I say, you can, on this cycloid pattern, you can go on, and we can spend all this time doing the math and doing the geometry. It's just a fun exercise if you like that kind of stuff. But here is one application that's pretty cool. Okay. It's called, oh, okay. So on this cycloid, blow this up a little bit. Can you see the blue inclined plane? Now there's a blue inclined plane there. I hate the colors, but, and there's red, okay, there's red marbles. And so we have three choices of how to get the red marble from here down to here, from the start to the finish. And between the start and the finish, you would agree that the shortest distance is a straight line, right? That's geometry 101. So no one's arguing that. But the shortest distance, the shortest time between here and here is not a straight line, but a cycloid. It's a cycloid flipped, a cycloid pattern flipped. And then this is called a Tadochrome. This is a Brachistochrome is the yellow, but the other blue is a Tadochrome. And this one is still slower. For some reason, well, there is a reason, but why, you tell me, why is that yellow? I mean, good grief, it's going up at the end. Why is that ball going down the yellow path faster than the ball going down the straight line? It's going the shortest distance.
Wouldn't its velocity pick up a lot?
The
Just by
velocity
going down.
does, yes, and a caveat here. But before, look, the only force involved here. Let's negate friction, okay? Because friction, the longer the path, the more the friction. So let's say it's frictionless. There's no thrust, okay? The only force, there's no wind or no air drag. The only force involved is gravity. If gravity is the only thing that's causing this thing to move, then you can make this, and it does work. But you're right. Look at this yellow. Right from the get-go, it's got, and Galileo called this dilution of gravity, right? He called it diluting gravity as an inclined plane. But from the get-go, the yellow path is getting a big shot in the arm of gravity, a big push, and it's front-loaded. The gravity is front-loaded on a cycloid on this. And okay, I'll show you a picture of it here. Here's another picture of it. Here, it's called a brachis. I said it right all day long. It's a Brachistochrome, one of the hardest words to pronounce. A Brachistochrome. But this, you can build these, and I've had students try and build them. They're good at building the wood. If you're good with wood, this first part is easy. Just build the inclined plane, but then you have to get a nice pattern for that and cut that out. The Brachistochrome or the cycloid. So you use a circle, make a cycloid, then you can cut it out. So the ball will always go down this path. It'll always go down this path here faster than it does this other path. But the reason is it gets just the right amount, a speed build up, early velocity, early acceleration. You have that. It's a combination of getting that velocity quickly, which builds up momentum faster. So you use that at a more timely period. Here is Adam from Mythbusters hooked up with Vsauce, and they built it in Adam's studio. He has a great, not really studio, his workshop. He's a great workshop, and I've shown this video in class before, but I'll link this video. But here they built it, and it's just fun watching these two guys. But they built the setup, and they were careful to kind of reduce friction down to nothing. And this is a snapshot of it. You can see that the disc that is sliding down the inclined plane is way behind. This other one's called a Tautochrome, and that's this version where you're really front line. I mean, the idea was, well, if we front end the gravity, then let's really front end the gravity. But what happens here is you lose out at the end, this little flat part. So this the Brachistochrome is the one that has just the right amount of gravity versus angle. And notice that it's probably at least twice as fast as the one going down the incline. So that has ramifications in energy, in shape, in airfoils, all these, because an airfoil is sort of uses a cycloid pattern on one end of it, depending on the kind of airfoil you have. So yeah, that's what we talked about today in class. I'm about out of time. Now all we have left to do is assign the homework. The homework this time is 7 and 8. Now for you all will turn in this whole sheet, but it'll be the end of next week. So we still have to go back and talk about drag again a little bit. We got to talk some more about lift. We got to talk about separation points and turbidity, currents. Got to talk about weight zones, all those kind of things. Still, that's probably tomorrow's discussion, and then we'll get into this rocket. Now, okay, I did have third hour start number 7, and in the 5 minutes they had to work on it, not one person had it right. Okay, so don't take it lightly. It's not that easy. There's a trick to that one. And this time now you have to do both y and x, which means you include sines and cosines. So you have to include sines and cosines on this one. So 7 and 8 is the homework, okay? And I've given you enough of a headache today. So you all are free to go. If you want to have a question, the bell just rang, and you can go, or you can stick around and ask a question.